All right, still everybody can see my screen, right? So we have 5 modules to cover today. Module 1 will cover the fundamentals of brushless permanent magnet motor design. Module 2 will discuss some of the motor and magnetic architectures. And module 3 will have analytical methods. I'm going to talk about, and I'm going to discuss with you my philosophy, how I view things in terms of motors and controls. And obviously, there is some amount of experience in it, and you may not agree with my approach, or you may find it interesting, but I'm going to leave that up to you to be able to challenge me and ask questions as we go along. Well, module 4 is introduction to space vectors, and module 5 is estimating motor parameters, right? So these are day 1 topics. And day 2 topics, we're going to cover mechanical considerations, which is, I think, an important part for every electrical engineer to know. We're not going to go too deep into it, but we're going to cover enough so that we can become dangerous as electrical engineers. We're going to talk about thermal analysis, power stage design, motor control problems and solutions, firmware development. So those are day 2 topics. And then day 3 topics, we're going to talk about stability analysis, finite element analysis, and then module 13 is finite element analysis using FEM. So those are the topics we're going to cover in the next 3 days, expected to be pretty robust. And hopefully I can keep you awake throughout the time. That'll be my attempt. Again, ask questions, be engaged, right? So we are ready to get started. Any questions before I get started? All right. If not, let's start with the very fundamental question. All right, so very fundamental question is, why does the motor turn? So here you can see a rotating motor. You can see green arrow, you can see a red arrow, or you can see a north magnet, a south magnet. And the question is, why does a motor turn? Anybody wants to answer that question? It's a fundamental question. I understand most of you already know the answer, but again, I want to just start a discussion with very fundamentals, because throughout our workshop, I'm going to go back to the fundamentals so we can analyze the complex problems from a fundamental standpoint, right?
Yeah, this is actually based on the principle, like if a current carrying conductor is kept in a magnetic field, it experiences a force. So going back to like DC motor, there we can very easily see these things, like if we have say some permanent magnet pointed towards say north south, so that would be basically, then we can go to our left hand thumb rule, where one is the direction of current flowing, other would be the middle finger would be the direction of current, then second finger would be the direction of magnetic field, and then the thumb would indicate the direction of the force, which is that would be appearing on that conductor.
Right. So the fundamental principle here is that conductor carrying current experiences force. Now, this conductor carrying current experiences force is, I call, a gift of nature. And that gift of nature, which we discovered, and we try to harness it in a number of ways, right? So here, what we want to further analyze, and thank you for that, Deepak. Now, we also want to look at how the current is distributed when we're trying to exploit the principle that a conductor carrying current is going to experience force. How do we arrange so that we can exploit in a rotatory motion, right? How is the current distributed? What are the 2 vectors? Which vector is leading, and what is the significance of that? How can you physically create this space relationship, right? So let's look at that again. So, or maybe I want to go back to the previous slide and give you a chance. So here, if you see, you have got distribution. You can see the red circles, and you can see a dot, and you can see a cross, right? And these red dots and these circle distribution seems to be rotating along with the green arrows and the red arrow, right? So what we have actually implemented in here, what is called the sinusoidal distribution. Sinusoidal distribution, magnetomotive force. Somehow we have managed so that the current is varying in such a way that it maintains what is called the red vector, right? So the green vector is being maintained by the magnets, and the red vector is being maintained by how we distribute current inside a motor, right? That's the ingenuity of our invention, is we are able to figure out how to distribute, how to have this interaction between the magnetic field and the current so that we can have a rotating motion. And fundamentally, as Deepak said, you have, this is one way to look at it. And I call this essentially, if you have a right hand and I point my flux density here towards the left, and I point my current towards into the paper, then I have a force which is vertical, right? And I'm going to assign these as d-axis and a q-axis just for the sake of our discussion as we go forward. All right. So any questions so far? Okay. Hopefully everybody's following me. If not, feel free to stop me. So now let's discuss the fundamentals of magnetic field, right? Now, again, magnetic field is a concept which we have developed as humans. We say, okay, we see these forces, we experience, once we invented electricity and once we were able to pass current through a conductor, we were able to see there's a force on a conductor. Then we came up with a concept to explain all of this. We came up with a concept called magnetic field, right? What is a magnetic field? It's a human concept where we say that it is the lines of flux. Lines of flux, we basically describe these lines of flux as magnetic field. And there we discovered further rules. The rules are that these lines of flux form closed loops. These lines of flux do not cross. And these lines of flux, when parallel to each other, repel one another, right? These are the rules we discovered along the way so that we can have better understanding of exploiting this wonderful gift from nature. All right. So we also discovered that magnetic fields have North and the South Pole. Again, all of these are human constructs, right? We discovered a principle in nature and we essentially developed a lot of theory and concept around it. And a current carrying conductor lying in a magnetic field experiences a force, right? Very fundamental concepts. Now, here, now we have a further math to talk about how these lines of flux interact, right? A varying magnetic field linking a circuit induces an electromagnetic motive force. We know that, we have learned it in a bachelor's. So a varying magnetic field linking a circuit induces an electromotive force called Faraday's law. And induced electromotive force opposes the change of flux, Lenz law, right? Very fundamental laws. And I'm building this foundation so that when we start talking about intricacies, we're going to come back to these laws very, very frequently, right? So if I draw a sinusoidal distribution of flux with time, right, then my delta, so this is a sinusoidal distribution and this is a sine function, then delta phi by dt, the cosine function. And then our change of flux, our change of electromotive force minus n d phi by dt is essentially our negative cosine function, right? And then these are the fundamental formulas we have. Right? We basically say force is equal to BIL. So B is your magnetic field. I is the current being carried by the magnetic field. L is the length of that conductor in the magnetic field. So that is also important. The force is proportional to the magnetic field. And then when you start thinking about motors and flux, these are going to be very useful formulas to come to. And the flux, we define flux as B times A. A is the area that encloses the flux. Flux density is flux over area, and then you have electromotive force being defined as BLU, where U is the rate of change. And if you have n number of turns, you have electromotive force as minus d n phi by dt. All right. So very fundamental stuff, and important for us to develop our further theory of motor operation. Any questions so far? Okay. So here is a very simple example in terms of if I have 800 amps of current being pushed through a 1 meter conductor in a 0.5 Tesla field, then I'm going to have a 400 Newton force, right? That's basically how we are now able to calibrate exactly how much force we get when we have a certain amount of current and certain amount of flux density using our formula. Now, we've gone through this. We basically say this is a cross product between current and B. If I use the right-hand rule, and it basically gives me that force, essentially. All right. Now, another aspect we want to talk about is when I have a current-carrying conductor of radius r, right, and I want to compute what is the flux density it is generating at a point small r, right, and r is greater than r, then we rely on what is called Ampere's law. Ampere's law says line integral of a magnetic field in a closed path equals net current enclosed, right? So from an engineering standpoint, if I were to look at a point away from the conductor, I can determine the magnetic field by using this formula, mu 0 I by 2 pi r, right? Now, we also introduce a concept called a magnetic field intensity H, all right? And now, why do we introduce a concept, magnetic field intensity? Because that is how we excite a magnet. That is how we oppose a magnet, we magnetize the magnet, we demagnetize the magnet. And we also say the line integral of this magnetic field intensity is going to be equal to the amount of current which is being enclosed by that path, LC. And we'll see how we're going to use these two factors in our motor design. And then let's define. B is our magnetic flux density. H is our magnetic field strength in ampere turns per meter. N is the number of turns. I is the current flowing in the path in amperes. LC is the length of the path through which current flows in meter. J is the current density in ampere per meter square. And then we have small incremental lengths dl and ds for the purpose of having the line integrals. Any questions? All right. So let's clarify what is the difference between B and H. So B is magnetic field effect. H is the magnetic field cause, the cause that essentially produces B. B is a field intensity. It depends on the field intensity and material. And H is only on current, depends only on the magnetic sources or current sources, right? Units, B is Tesla, H is amperes per meter, and formula, B is mu, which is mu, the permeability of a material, and times H. And of course, that's the reverse of that formula. Affected by material, yes, flux density is affected by material. Field intensity is not affected by the material, all right? So again, some more formulas here. The most important formula is that we introduce a concept of reluctance. So we say that if you have magnetic field intensity, which is basically Ni, then that can equate equal to R phi. All right, so let me go line by line so you guys can follow. I don't want to jump around. So magnetic flux in the cross section of a core is given by phi c equal to BCAC. C stands for the core, where phi is a flux in the core. Magnetic flux density is defined as B equal to mu H, where mu is the permeability, given by mu equal to mu zero. Mu zero is your permeability of air, and mu r is your relative permeability. So the flux can also be expressed as phi is equal to mu h times A, which is equal to mu times Ni times A divided by L, and then it is equal to Ni by R. All right, and I have sent this out, the PowerPoint. You guys are welcome. Recording also will be available. You guys are welcome to go through these as many times as you want. So the concept of reluctance is important because that allows us to figure out how the flux is flowing through a magnetic path. So reluctance is equal to L by mu A. Ni is defined as magnetomotive force denoted as F. Flux can also be written as force divided by reluctance. This is where we begin to define how the flux flows through the magnetic paths. And we say magnetic circuits are analogous to electric circuits, right? This is a big leap where we have a revelation that we can actually use the same laws we use in electric circuits to analyze magnetic circuits. So an electric circuit, you have a DC source, you have a current, you have a resistance. Magnetic circuit, you have magnetomotive force, you have the flux, and you have the reluctance, right? Now, and here you have an equivalent. Electrical circuit, mu is equal to IR, F is equal to phi R, and then you have sigma as the conductance, and then you have here, sigma is the conductivity, not the conductance, the conductivity of the copper or the material, and then mu is your permeability. So resistance, reluctance, L by sigma A, R is L by mu A. Very similar concepts in terms of magnetic circuits versus electrical circuits. Then also Kirchhoff's voltage law and current law are applicable in the magnetic circuits. All right. And welcome to stop me at any time if you have any questions. All right. Now, here is another, again, fundamentals. If you have, this is a core, magnetic core, and you basically have put two coils in it, right? And you have got the gaps in the core. Here, and how do you transfer this into a magnetic circuit you can analyze? So basically, you're going to replace the coils with a force, F1. You're going to replace the air gaps with the reluctance, RG1, RG2, RG3. And then you have this force being replaced by another magnetomotive force. And your directional current basically decides, if I'm using the right-hand rule, my flux is going to go up in this coil. So I have a plus here. Here, it's going to go down. So I have a plus down there, right? All right. Now let's introduce one more concept. Another important concept we call flux linkage. And flux linkage is a very interesting concept because when we talk about, especially in a motor, when you look at a coil, and you want to say, okay, I want to understand what is the flux linking that coil. And there is a flux produced by the coil, and there's also a flux produced by other coils surrounding that coil, and there's also a flux produced by the magnet, right? So we come up with a concept called flux linkage to really characterize the behavior of the coil. So that flux linkage is called lambda equal to n phi. So if you have n number of turns in a coil and all the flux together is called phi, we say, okay, it has a flux linkage of n phi, right? Now, if you have two coils, you can say, okay, I want to look at its own flux, and also I want to look at the flux being shared by a second coil. We call it lambda 1, 2, right? So you have a self-inductance and you have a mutual inductance, or you have a self-linkage and the mutual linkage, just sharing of the flux from the other coil to the coil 1. Similarly, we have similar equation for coil 2, right? So now along with the flux linkage, I want you to understand the concept of inductance, right? Inductance, and we'll drill down to what inductance actually means. So we further define a concept called inductance by using this formula called N phi by I. So basically, we take the current flowing in the coil and divide by the total flux linkage, and we get this term called lambda divided by I. All right. So now we can define the flux linkage in terms of these inductance values, right? So what we did is essentially same equations, we have substituted the inductance values here. All right. Now, what comes out in a simple circuit is if you look at the inductance, it comes out to this formula, mu n square A by L. All of these are constants, right? So inductance becomes a geometric measure of a magnetic circuit. Now, you can have saturation, yes, and you can have permeability changing. So inductance can change because of the issues of current, etc. But in a linear zone, inductance essentially becomes a measure of the geometry of the magnetic circuit. Okay, and that's an important value to be able to look at a motor circuit and be able to evaluate the motor circuit. Now, another parameter which defines the geometry of a magnetic circuit, of course, is the reluctance, which we talked about. And the relationship between inductance and reluctance essentially is L is equal to N squared by R. Inductance is inversely proportional to reluctance. All right, any questions so far?
What do you mean by geometry of magnetic circuit?
Good question. So this is, I would see how, all right. So when I talk about geometric parameters, essentially what I talk about is number of turns, area, length. They're all constants, right? And if you consider mu as a constant in a linear zone where it's not changing or not saturating, you essentially have no variables. It is inductance basically defines a geometry, right? That's what I mean by geometric parameters or geometric, it's basically a dimensional value. Does that make sense?
Okay. Yeah. Thanks.
Yeah. All right. So okay, we discussed that. So let's go to the next one. So here is an important question, right? So now let's get a little bit more complicated. If I have a magnet placed in a magnetic circuit that also includes an air gap, and I assume there is no flux leakage or fringing, will the magnetic flux density stay the same throughout the whole path, including through the magnet, the core, and the air gap? So let's say you take a magnet, you put it in a core, right? And let's say your core has an air gap, and assume there's no flux leakage or fringing. So will the magnetic flux density stay the same throughout the whole path, including through the magnet, the core, and the air gap, right? So this is one question we're going to wrestle with. And let's look at the problem, all right? So this is the problem. So what you have on the left-hand side, this is your core, okay? And we're going to assume it has an infinite permeability. We have n number of turns. We are flowing a current IT. We have a magnet here of length d. We have an air gap of 4 millimeter, gap area of 500 millimeters square, and n is 250 turns. What you see on the right-hand side is the second quadrant of a BH loop of a magnet. Now, what does it tell you? So magnet, and we'll talk about magnets in more detail, but here what you're seeing is you're seeing a BH loop of a magnet in a second quadrant where it says that magnet in free air is going to give you a flux density of 0.4 pi Tesla, okay? And if you were to if you wanted to demagnetize this magnet, you're going to, you will have to put magnetic field intensity of minus 10 to the power 6. Then the B will go to 0, right? Now, this is where the magnet operates in a motor, in a second quadrant, right? That's what we exploit in the motor. When the magnet is in the motor, it's operating in the second quadrant of the BH loop, okay? And we're going to exploit this. And you can see it's a pretty linear slope. Thankfully, it's a fairly linear slope, so it makes our life a little easier, okay? So now, let's define the problem. So let's say in the air gap. So let's go back to the problem, and this is the air gap, okay? Here, 4 millimeter air gap. So what we want to say is, sorry, okay, so I have air gap flux density of 0.5 plus 0.25 sine omega t. And we say 0.5 Tesla is created by the magnet. 0.25 Tesla is created by the current. And we need to find D and I. So this is a homework problem. I would like you to, everybody has a copy of these slides, and I'd like you to attempt and perhaps come back with an answer tomorrow, is what you believe should be the values of D and I. I'll give you some hints on this one. So here is a model for the magnet you want to think about. Okay, so this is our magnet of length Lm, of flux density Bm, and area Am. And we are going to assume that when we have it in the magnetic circuit, it is operating at a magnetic field Bm. Okay, now here, because this is a linear slope, we can basically say Bm is equal to mu m Hm plus Hc. All right. And here is another model I want you to consider. This is now the HMLM being the magnetic field intensity being applied by the current on the magnet. That's why it is in the opposite direction. Okay, this is your magnetic model where you have your no load flux density being, essentially you have the HCLM as your magnetic field intensity force. You have the reluctance of it. Okay, so combining these two, you essentially come up with these equations, HMLM equal to RMPM minus FM. All right, so your goal is to use these formulas and figure out what is the value of D and I. Okay, so that'll be the homework problem for, so what is the value of D and what's the value of I, right? Any questions so far? Okay, so let me forward. All right, so let's talk about, now this is some of the practical stuff, right? Basic design considerations and motor design. Now, motor design can become very complicated very quickly because you can have a lot of conflicting constraints to manage. So let's look at some of the requirements our customers will ask us. They will ask us for, they want to have maximum torque. They want to have a very lightweight. They want to have a motor that doesn't really, has a very small size, maximum power output, no noise. You also have, you have specifications of bus voltage, what's available to you, what speed you need to produce, what is the rated torque, and number of phases. And that's one of the choices you may have, you may not have. Majority of the motors are three-phase motors in the world. Number of poles, number of slots. Now, number of poles and slots become critical when it comes to manufacturability. You cannot really, although you may have a perfect design, but you can't manufacture it, it's of no use. Air gap thickness, again, very, smaller the air gap, the better is your torque production. But then again, you cannot produce a very small air gap motor. Motor aspect ratio, maximum outer diameter, maximum length. So these are some of the constraints we have to wrestle with when we are talking about designing a motor. Again, you have further considerations, rotor location. Most of the motors have got rotor as inner part of the motor, inner rotor location. Rotor type. What kind of rotor are we looking at? We'll talk about rotor architectures in the upcoming slides. Rotor temperature, another important part, because as the temperatures go up, magnetic material properties go down. Another important part, very crucial part when you're looking at all of a sudden your motor doesn't produce torque or power. Why is it? We need to keep in mind the rotor temperature is a critical part. Rotor magnet material is another critical part which can be impacted by the temperature of the rotor. All right. Similarly, stator type, stator temperatures. Now, stator temperature has an effect on the permeability of the material and also has an impact on the resistance of the material, of the coil. Stator coil material, some of the motors are produced with aluminum wire. How does that affect? And you have to take into consideration aluminum versus copper, and that comes into play. So, and then there is more sizing parameters we have to look at. Torque per unit volume. That is a measure of how good your motor design is. Rated current density, fill factor. Higher the fill factor, the better is your motor performance. The rotor stator diameter ratio, stator flux density. Obviously, if you can maximize your flux density without saturating the material, you're better off. You're using the materials better. Back EMF limit. You don't want a motor to overspeed where it's going to destroy your drive. So there's a back EMF limit. Magnet air gap ratio. It's a measure of what is your magnet thickness with your air gap, and the magnet coverage, how much of your circumference is covered with the magnet, right? So important design considerations as well as constraints. Now, you also have constraints about the design of the controller. Sometimes you have a space limitations of the controller. Sometimes you don't. Most of the time, you have larger drives. It becomes a bigger issue. If I'm using 400 kilowatt drive or 500 kilowatt drive, and it weighs, it's a 6 feet tall and 3 feet wide and 2 feet deep, you have to think about where to install it safely. Okay, location becomes important, control methods become important. All right, and then we also have to consider for the motor part whether it's geared or gearless, because ultimately overall efficiency of the powertrain from input of the power supply to the work being done at the output, you have to consider overall system efficiency, and you have to take into account also the mechanical interfaces, right? Whether there are brakes, whether the cogging torque is an important aspect or not, because cogging torque can also cause a lot of issues in terms of performance. And then, of course, we have to think about manufacturing considerations, which is very important, because if you make a motor very simple to manufacture, it may not be as efficient, right? So there's always evolution of manufacturing methods versus the design we want. And there's certain very clever manufacturing methods where we can achieve both. But most of the time you see that manufacturing concerns, basically you design the motor which can mass produce. And as a result, you have to dumb down your design as long as it meets the customer requirements. Lamination methods in design, magnet methods in design, all of these take into play, your cost considerations. If you're looking for consumer-oriented product, you may have a lot of pressure for price. If you're looking for military or application where you have more of a performance pressure than the price pressure, right? So all of these thermal limitations, metal housing plus cover method, all of these come into play in creating a great product that can be manufactured. So I'll stop here and see if there are any questions I can answer.
Hello, sir.
Yes. Yes,
So
go ahead.
the design constraints that you talked about, this bus voltage, rated speed, and torque of the motor, How can we relate these terms with automotive? I mean, you can say e-rickshaw, passenger cars, or two-wheelers. Their acceleration and deceleration profile, or you can say drive cycle. How can we relate that?
Yes, that's a very, very good question, Simran. So, and it becomes more critical in those applications because if you're able to, if you use a motor then that can produce substantial amount of back EMF, then one advantage is, okay, the battery will absorb, if you are going into regeneration, battery can absorb some of that. Okay, but the battery has also limitations. Lithium ion battery cannot absorb limitless regeneration. Lead acid batteries, cannot generate limitless regeneration. So what you have to watch out for is so the most important part in automotive is your regeneration well controlled? And that's an important part, right? This is where your back EMF limit comes into play as well, is okay, I also want to exploit the bus voltage to get the maximum performance. Okay, so because I can only, and we'll look at the equations in the upcoming slides, but your bus voltage utilization is very important, right? So if you're not able to utilize all of your bus voltage to get the maximum speed, maximum torque, maximum power out of the drive, then you're not being efficient in your design, right? So the two aspects you have to take into account is you're using the space factor modulations, and also making sure that your motor, essentially your base speed, the base speed of the motor utilizes all of your bus voltage, and you're able to get the maximum torque and power, because at the base speed is where you deliver maximum power and torque, that comes at the bus voltage point. And then your regeneration cannot be such that it will overpower your battery or exceed your battery voltage, which can damage the inverter you are using. Does that make sense, Simran?
Yes, sir.
Okay. Thank you for your question. Any other questions? All right, so I'm going to just take a very quick example here where, let's say we have a bus voltage of 24 volt, a rated speed of 155 RPM, a rated torque of 22 Newton meters, right? Very simple. We start with these specifications and see where they lead us, right? And here we define, okay, we're going to go with the number of phases is 3, number of poles is 28, number of slots is 24, air gap thickness of 1 millimeter, motor aspect ratio of 0.1. Basically, that is the length divided by the motor diameter. Okay, it's 0.1. You have rotor location. You're saying, okay, I want to have rotor which is outside. I want to have a surface mounted rotor with radial magnets. I want maximum temperature of the rotor to be 50 degrees Celsius. And rotor magnet material, neodymium iron boron, energy product of 36 MGOE. Now, magnets come in a variety of energy products based on your temperature, cost, etc. So here we're saying we're using neodymium iron boron 36 MGOE magnet. Okay. Stator. We want a square type stator. We'll discuss what a square type stator is in the upcoming slides. Stator temperature of 100 degrees Celsius max. Stator coil temperature. Stator coil material is copper. So we don't care about torque per unit volume at the moment. We don't care about rated current density.
Sir,
Yeah.
I want to ask you a question. You said the rotor is external.
Yes.
External means, can you show any diagram how the rotor can be external?
Yes. So let me show you. Here, give me a minute. Let me go through this, and then we'll come up with a picture here, Simran. You should be able to see how that is.
Okay, sir. Thank you.
Yeah. All right. So we're going to say rotor stator diameter ratio is 0.65. So that means rotor is bigger than the stator. Stator flux density is 1.2 Tesla max. Back EMF limit is 0.9 max. Magnet air gap ratio is 3.5. So if you have a 1 millimeter air gap, you're going to have a 3.5 millimeter magnet air gap, magnet thickness. Magnet coverage is 0.95, 95% circumference you're covering with magnets. And then you want to have a small controller. So maximum current we can push through the coil is 50 amps. Location is internal. We want to use field-oriented control plus space vector modulation. Okay. So gearless, no brake, very low cogning torque. So in terms of winding type, method, and design, we want to use something called fractional slot concentrated winding. We want to use, I don't remember the lamination type. I think it's M50 or something. Magnet type, neodymium, iron, boron. Shaft is made of steel, mild steel. You have aluminum housing, aluminum cover, and then you do have thermal limitations, right? So what does it lead us to is something like this. This is the motor, which essentially is your outer rotor motor with axle being fixed in the middle and the stator is inside. Okay, are you able to see that, Simran?
Yes, sir.
Yeah, does that make sense?
Yes.
Yeah, so this is not a very favorite motor. I would say 99% of the motors in the world are with inner rotor. Now, this again, some unique applications. For example, this is an application for an electric bike where it makes sense to have an outer rotor motor because you can attach spokes to the outside of this motor. All right. So